Hello everyone, and welcome back to another video. And today I was a little bit, I'll admit it, I was a little bit bored, so I went on to Math Stack Exchange, as one does, and I found this that was posted today, which I found to be quite interesting. So I had a crack at it, and yeah, that's what this video is, my crack at this integral, my attempt. So let's get started, shall we? I'm just going to begin actually by just writing out sine in terms of its power series right here, with the a square root of x, of course. So it's just going to be equal to the sum from k equals 0 to infinity of, instead of just x, we're going to have a to the 2k plus 1, but then also times x to the k plus 1/2. And then, we're going to have our negative 1 term. Then we're also going to have our 2k plus 1 factorial term in the bottom. And we can expand this series out for sine. But the real reason for doing so is, it might be a little bit subtle, but you'll notice that we have a 1 minus x to a power here, and then we have an x to a power here. What we can do then basically is just use, apply the beta function, because we also have an integral here from 0 to 1. So that's really just what we're going to do next. And of course, we're just going to rearrange the order of the sum of the integral. And yeah, let's evaluate the integral, and then we'll deal with the sum of what's left. So just in general, what we're going to have is the sum from k equals 0 to infinity. I don't think I'll write the bounds for the sum anymore. It's always going to be from 0 to infinity from now on. But what we have is an a to the 2k plus 1 divided by 2k plus 1 factorial times negative 1 to the k, of course, that is all of our terms, times the integral from 0 to 1 of square root of 1 minus x times the x to the k plus 1/2 dx. And now just to kind of zoom in on this integral bit right here, again, this is just the beta function. So this is just going to be beta of 3/2, but then also k plus 3/2, which is probably one of the more ugly beta function expressions I've gotten, but that's okay, it'll simplify enough. But again, we can just write this in terms of the gamma function by properties of, or I guess almost definition. Properties of the beta function, sure. Anyway, we have gamma of 3/2 times gamma of k plus 3/2, and then divided by gamma of, well, we're just going to add these two terms, right? So it's just going to be k plus 3/2 plus 3/2, but 3/2 to 3/2 is 6/2, which is 3. That's how fractions work. So we just have a gamma of k plus 3 here. So to sub this rather ugly expression into our integral, but before we do, I am just going to note that this right here is just constant. This is just square root of pi over 2. Nothing, I say nothing special. It's really cool, but it doesn't have a k in it, so in that sense, it's not that special. So yeah. Anyways, to write out our entire series now, what we have, this is going to equal to the sum of a to the 2k plus 1 over 2k plus 1 factorial times negative 1 to the k. And then we're going to have our expression in terms of our gammas. So we're going to have gamma of k plus 3/2 over gamma of k plus 3. Oh yeah, and then we have our square root of pi over 2 out front. It is important, but it's a constant, so we're just going to factor it out of the sum real quick. And this is the sum we're left to evaluate, which, albeit is incredibly, I'll say it, ugly, it is technically doable. And the whole idea kind of lies in these terms right here. I'm just going to focus on these three terms, basically everything with a factorial or a gamma. And we're going to simplify that down a bunch, and then we're going to compare it to a known series and go from there. So I'm actually just going to write this off to the side, just for the sake of keeping things neat. So what we have is a k plus 3 halves, a gamma of k plus 3 halves over 2k plus 1 factorial, and then we also have a gamma of k plus 3 in the denominator. I did get that right. That's good. So the identity that we're going to be making use of here involves the gamma function, namely gamma of 1/2 plus n is equal to 2n factorial divided by 4 to the n factorial times the square root of pi. And on the surface, this really doesn't seem like it would be helpful. After all, well, we have a gamma of, 1/2 plus n here, and well, that's a 3/2 up there. But as one says, trust the process. No, I'm slightly kidding, actually. But in all seriousness, what we can do is say, well, what if we consider n being equal to, say, k plus 1/2? And what that basically does is just we're shifting over our n a tiny bit. But the main thing that allows us to do is get a k plus 1/2 factorial term in the denominator there. And k plus 1/2 factorial, well, just by definition of the gamma function, really, is just gamma of, k plus 3/2. So we can solve for it that in that kind of obscure way. But the reason why it's so nice is, well, really for the following reasons once we plug in this n. So I'm just going to put that out of the picture slightly for now. So once we plug in, n being equal to k plus 1/2, well, on the left-hand side, we're just going to have gamma of 1/2 plus 1/2 plus n, and that's just 1 plus k, which is rather nice. And on the numerator, we're just going to have a square root of pi, of course. But then we're also going to have a 2n, but n is just, k plus 1/2, so that's really just n plus 1, 2k plus 1 factorial, which you'll notice will cancel with that in the denominator there. And what gets even better is that, well, this is kind of the whole point of why we did the substitution to begin with, but we have a k plus 1/2 factorial term in the denominator here, and then we kind of just have this 4. I'm gonna be honest, we have this 4 just kind of sitting here. It shines a little bit later. But anyway, the point is that, well, we can just swap these, really. Do a little bit of algebra. And what we find then is that this expression here, is that this numerator part is just equal to, so gamma of k plus 3/2 is just equal to the square root of pi over 4 to the k plus 1/2, but then times 2k plus 1 factorial divided by k factorial, and that's just gamma of k plus 1. So then what we're left with is, you'll notice, well, let's just look at what cancels. The only thing that does cancels. That cancels with that, meaning we're left with the square root of pi over 4 to the k plus 1/2. And then I'm sure another fraction bar for like factorials and gammas. K factorials times gamma of k plus 3. But then in our numerator, well, we're not going to have anything because it just cancels out. So that's what we're left with. And you'll notice that we've simplified everything quite a bit. So let's just rewrite everything, maybe factor out a square root of pi, and let's just see what we have in all here. So factoring out that square root of pi, what we're left with here is a pi over 2, our sum of, that's a big sigma, times our sum of a to the 2k plus 1 over k factorial times gamma of k plus 3. That little bit didn't change. Times -1 to the k, of course. And yes, we have our, let's a little bit. We have a 4 to the k plus 1/2. And in all honesty, this doesn't look very nice. But I'm just going to do one last simplification. This is going to be equal to pi over a. And the reason for that is just I kind of want to get this term right here and this term right here just under one exponent, just for the sake of, you will see. So sum, and we're going to have, we're multiplying the top and bottom by a. The top one is going to go to the a to the 2k plus 2. But, I mean, we're going to want to write this into being divided by this 4 term right here. So this right here is just 2 to the 2k plus 1. But we have this extra 2 here, so we're going to get an extra plus 1. So that's why we're doing the whole a thing right there. So it's just an a over 2. And then we have, you know, the rest of our fraction. We have a negative 1 to the k over gamma of k plus 3 times k factorial. And right now you might be thinking, this is incredibly ugly, and where on earth are we going to go from here? And my answer to that is really just invoking the series definition of the Bessel function of the first kind, to be specific. And the reason for that is really just for the following. The Bessel function of the first kind, so j alpha of some x. This is just, it's not necessarily defined to be, but whenever you apply a certain method to Bessel's equation, this is the series solution you get. I'm using the notation Wikipedia uses just for the sake of consistency, I suppose. Negative 1, or actually, well, not for consistency, but I have it in front of me, okay? But anyway, this is just the definition of the Bessel function. If the sum from m equals 0 to infinity of negative 1 to the m over m factorial times gamma of m plus alpha plus 1, and then times x over 2 to the 2m plus, scoot the screen over, I thought I could fit it in, alpha. And you'll notice here that there's a lot of parallels, and by a lot of parallels I mean it's nearly identical. The only thing we really have to worry about is that, well, we leave the constant out front, but you know, we can deal with that. But just in terms of the series, you'll notice that, well, we have a 3 here, and we have a 2 up there. And that's not really an issue. And the reason for that is because, well, if we just say alpha is equal to 2, then what we're left with here in the denominator inside the gamma is, well, 2 plus 1 is 3. What we're left here in the numerator, or in the exponent, sorry, of this x over 2 term is just, well, 2m plus 2. And that's exactly what we have. And what this just means, and I mean, then of course there's the parallel between the a and the x here, I mean, but yeah. So what we're left with here is really just pi over a times the Bessel function of the second kind, or sorry, of the first kind, or j2a, or j2a, yeah. There's the Bessel function of the first kind, the subscript of 2 of a. And that right there is just our answer. I know I butchered the pronunciation of the Bessel function. I'm sorry, but the answer here still remains. And basically, that right there is just our answer. It's just pi over a times j2a. Well, it kind of rolls off the tongue, doesn't it? Anyways, I hope you all enjoyed this video. This is kind of like my first time messing around with the Bessel functions. I had a lot of fun with it, and I hope you all enjoyed. And I'll see y'all in the next one. Physics Friday will hopefully be out soon. Adios!